Ladies and gentlemen, distinguished guests, welcome to the 7th Samsung AI Forum afternoon breakout session. My name is Jin, and it is my great honor and pleasure to be here as your MC today. 먼저 인사드리겠습니다. 안녕하십니까? 저는 삼성 AI 포럼 오후 브레이크아웃 세션의 사회자로 함께하게 된 조진경이라고 합니다. 반갑습니다. Today's CE presentation or session consists of 1 plenary talks, 2 different sessions focusing on large-scale computing for LLM and simulation. After starting off with the plenary talks by Mr. Satoshi Matsuoka, 3 different speeches will be delivered by Mr. Zaid Kahn, Mr. Masato Motomura, and Mr. Joo-Young Kim. I believe that you'll be able to take away valuable insights through the presentations that we have prepared today. Then, without further ado, I'd like to kick off the plenary session by inviting Mr. Satoshi Matsuoka from the RIKEN Center of Computer Science. He'll be presenting on Fugaku and FugakuNEXT. What matters in supercomputing is bandwidth, not flops. Ladies and gentlemen, please greet him with a big round of applause. 큰 박수로 맞이해주시기 바랍니다.
Well, thank you for the kind introduction. I'm Satoshi, and I'm super glad to be here. Very honored to be back in Korea after COVID, because I always like visiting Korea. Today I'm going to talk about supercomputing, because now the modern AI, as we know, is driven by big machines. As much as AI is self-wonderful, supercomputing we've been doing for the last 50 years. But what the advances we've made now is finally enabling these ultra-smart AIs to be present, including, like, for example, ChatGPT. So I'd like to talk about the machine, but also how it evolves and how AI will evolve even further, especially in its application, AI's application to advanced science, because we have always built these machines to advance science, right? Like with simulations, but now the AIs that we enabled by these big machines will enable new breeds of science, new discoveries, new innovations in science in a way much more beyond what the traditional simulations have done in combination with the simulation, okay? So that'll be my talk. So firstly, this is a machine that we have developed, Fugaku, which we have worked for, including me, we have worked for the last 10 years. Now it's in production. It's been working since 2020, for 3 years now. We can't capture this machine in a single photo. It's very difficult to do that. In fact, the machine is like this big. It occupies about 3,000 square meters. Has 432 cabinets. It has 158,976 nodes, okay, about 160,000 nodes, or about 8 million CPU cores. On average, uses about 16 megawatts, but maximum it can use about 30 plus megawatts. It has 163 petabyte per second memory, et cetera, et cetera, et cetera. So it's like a hyperscaler data center, but it's one machine, one big supercomputer. Okay, and so far today, it's the largest supercomputer ever built in the world. So why is it named Fugaku? Well, because these modern supercomputers, we want it not just be capable, very tall, but also very broad, be applicable to a variety of applications used by many people in various branches of science and industry, and also to connect to the rest of the IT. So, Mount Fuji, or national mountain in Japan, sort of signifies that, because not only it's the tallest mountain in the world, in Japan, but also has a very broad base. One of the unique mountain being a singleton peak doesn't have too many high mountains around it, and that's why it has a very beautiful, widespread base. I'm sure that some of you have visited Japan and looked at Mount Fuji and also looked at its beauty. So, the shape of Mount Fuji expresses our idealism towards supercomputing that is both tall and broad. But of course, it's much easier said than done. Building anything that's high performance in any area, not just computing, but let's say in automotive, okay, and like building cars, but also very wide, very broadly applicable, is very hard. It's a very, very difficult challenge. Let's say if it's a car, it's like building a car, design a car that can race like a supercar, right? Very, very fast, but you can go to a supermarket with, which not many supercars can go to supermarkets. So it was a big engineering challenge, but the entire community of Japanese FugakuNEXT collaborators, including those in Korea, like Samsung, these memory chips you see on the side, these are Samsung HBMs, so Korean technology right there, along with many other technologies worldwide. But basically, Fujitsu and ourselves we designed this big supercomputer lasting 10 years as part of our national project, and we built this processor, which is compatible with ARM instruction set, so it will run any program that you run on your smartphone, but compared to any server processor of the time, was about 3 times faster or 3 times more power efficient, partly in thanks to high memory bandwidth realized by HBM2, Samsung's HBM2. So if you put this Fugaku in context, it's equivalent to about 200,000 smartphones you have in your pocket, which runs the same program, but nonetheless, 200,000, about 20 million smartphones. And 20 million smartphones is about how many smartphones are sold in Japan annually. So if you take one single Fugaku, it's equivalent to all the smartphones sold in Japan. Or if you take several Fugakus, it's equivalent to the entire compute capability of Japan. Okay? So that's how big these machines are. So this is a processor design with Fujitsu. So it was the first 7-nanometer server chip. Again, it was about 3 times more power efficient. In production, this chip combined with HBM runs at 100 watts on the average per node, which is about 1/3 what you might expect out of, let's say, Intel Xeon. But it's, again, entirely compatible in the ARM ecosystem. A lot of people, when we say ARM, they make a mistake saying, well, did you get the ARM IP for the cores? No. The only IP we got from ARM was the instruction set. Everything inside, the microarchitecture, everything, Fujitsu and us, we co-developed. So we have no ARM IP with respect to the microarchitecture. The other characteristics is it embeds a 400 gigabit class network inside the chip, not as an external NIC. So this allows us to scale to 160,000 nodes, but very, very fast communication. And in fact, not only it embeds the network processor, but also incorporates the network switch. So if you look at Fugaku, there are no big director network switches because all the switches are embedded inside the chip on the left-hand corner. So there are 160,000 nodes, but also this machine has 160,000 network switches. Okay? And it has other salient architecture features, which I want to mention. But this machine, again, has been running in full service, full capacity for the past 3 years. So this is how it looks like. We have 384 nodes in a single cabinet. So we put two nodes in a single board. There are 192 boards in a single cabinet. So if you look at a typical data center, you may, or even with some of the more dense architectures, you may only have like maybe 40 to 60 to maybe 90 nodes in a single cabinet. This is at 384 nodes. So despite the fact this humongous size of the machine had you built it out of a standard data center components, even with OCP, the area would have been more like 10,000 or even 20,000 square meters. Okay, so it would have been humongous. Okay, so here's the catalog spec for those all you tech nerds out there. It is sort of an exascale machine. It won, has all the specs. It's got lots of accolades. It won the Gordon Bell, what's called the Gordon Bell Prize twice, which is the most esteemed prize in computing, in supercomputing in terms of applications. It provides 1.3 billion node hours of service time to the entire world, and we have collaboration with many global institutions. If you're interested, you could just Google Fugaku instead of just clicking on the website. Okay, so in terms of ranking, supercomputing is one area where people like to compete. Right? In fact, that's the area where performance is the ultimate. So there's a global competition that's been going on for the last 30, 40 years. And during 2020 and 21, there are various benchmarks, just like in the Olympics. You have different types of competitions. There are several types of rankings, not just one. And in 2021, Fugaku was #1 in all metrics. Now, of course, other countries have excellent technologies, in particular the United States, and they're the global leaders still in supercomputing, so they have sort of came back, and now the top ranks are shared with the machine in the United States called Frontier at Oak Ridge National Labs. So that relegated Fugaku to be #2. But the point is not to be #1 in all of these. The point is to be balanced. Like I said, Fugaku is Mount Fuji, and if you're Mount Fuji, you're supposed to be very broad. If you're very broad, you're supposed to excel in all the benchmarks, not in just one. So one thing in our business, what we avoid doing is to build what's called a stump machine, right? Which is only good in one metric, right? And not very good in others. But some people actually do that. And the fact that we have this very broad applicability, and and other people who build these systems in other countries, because they're also as capable, they build these broad systems, is one of the reasons why AI has taken off by being applied to these very large machines, because machines had sufficient flexibility to serve the needs of AI workloads. In fact, there is an AI benchmark, XPL MXP, and also MLFF HPC, which are now one of the most important benchmarks in this very high-end AI. But actually, Fugaku was not designed to excel in benchmarks. It was designed to solve real problems, real hard scientific problems, real problems that affect the societies today. Problems like your health, pharmaceutical, medical, things like environmental, global warming, climate change, disasters, typhoons, earthquakes, things like, and carbon neutrality, energy, right? So energy production, carbon neutral energy production, energy storage, energy transmission, manufacturing, Korea, Japan, we're all about manufacturing, from material science, materials, all the way up to things like gigantic ships. And of course, there's basic science as well. So the way Fugaku was designed is not to excel in a single benchmark, but designed to excel in these real applications to solve the hardest and next generation problems. And to achieve that, achieve orders of magnitude speed up over our last machine, which was called a K computer. So if you look at the 120x, or 100x, or 70x, the overall target of the new machine Fugaku compared to the K computer 10 years ago to achieve close to 2 orders of magnitude speed up in these very important problems. That was the objective, not the benchmarks. Okay? And as you see in these numbers, we have achieved that. We've achieved an average of almost 70x performance gains in real applications to solve these hardest problems. Okay? So that was the goal, not excel, not to be #1 in, let's say, the top 500 benchmark. That was only consequence, not the objective. Okay? That's very important. Okay, so one of the earliest, so what are the problems have we solved? So one of the most difficult challenges that faced us was COVID, because as Fugaku was starting to be manufactured, late 2019, early 2020, and started being installed on my premise, what happened was COVID. COVID happened and quickly shut down the entire world. So obviously we had a lot of challenges with respect to things like supply chains and building the machine itself. But the other difficult challenge that we wanted to solve is now that the machine was slowly being stood up. We saw the opportunity that we can really apply our technology to practice, because as the machine, as I said, these are application areas, and there were applications that was being co-developed along Fugaku. So development of Fugaku was not just about developing the machine. It was about developing the applications, algorithms, applications, and the sciences. So when Fugaku was ready, the applications will be ready to use them. It wasn't as if we would build a machine, and then then the scientists will start using it 3 years, 4 years later, they'll get the results. The project was designed so that it wasn't just the hardware development, software science development happened in parallel so that it will meet at the right junction point when the machine is deployed. And this happened to also coincide with COVID. Okay? So what we did was to propose to the ministry, and also what we did was to stand up the program to use Fugaku's resource, which was quickly becoming the fastest machine in Japan by far, to apply this humongous computational power to solve problems in COVID from the very fundamentals, from the atomic levels, all the way up to the societal levels, like what kind of impact would shutdown have. Okay? So I won the Gordon Bell Prize for one of this, and I'll especially focus on one particular application we did, which won us the prize, which was the aerosol simulation. Because we knew from very early on there was a big suspect that COVID was being transmitted as an airborne disease. But a lot of experts denied that. Some experts came on TV in Japan and said, I will not be wearing masks because we're not needed. I said, what the hell? What the hell? I mean, that doesn't make sense. But there was no scientific evidence, and when we talked to the experts, at scientific institutions, there are a lot of people at RIKEN trying to solve the problem, and but they were not conclusive either, because when we talked to epidemiologists or virologists, they couldn't just do the experiments, and they didn't have the simulation capabilities. So we said, okay, but one of the applications that was being developed for Fugaku was like this way beyond the state-of-the-art computational fluid dynamics, multi-physics computational fluid dynamics, which were designed for industrial purposes, like designing advanced CFD for turbine engines or automobiles, or simulating city airflows and thermal condensation cities, and also applied to something like combustion engines. So, so if you're interested in stuff like combustion engines, we all know that these combustion, the piston goes up and down, you have a manifold, the air comes in, and there's a fuel injector. Okay? And a fuel injector would spray the fuel into the chain, out of the manifold, or directly onto the combustion chamber. So one of our scientists on this team noticed, on this CFD team, so they're building this way beyond what the commercial packages can do, like tens to 100 billion degrees of freedom CFD. That this spray patterns of this fuel injection is exactly the same in terms of physics as someone coughing or singing loudly in karaoke or something like that. And then the aerosols, the droplet aerosols spewing all over, which would be invisible to the naked eye, but exactly the same physics. And these aerosols containing viruses that will stagnate in the air for hours if you don't have proper ventilation or not wearing masks. That's the source of transmission from one human being to the other. When we, again, consulted with the epidemiologist, they said, well, maybe, but don't quite know. So we said, we'll team up with them, show them this, and said, yeah, this is it, but we lack the capabilities. So we went on, because we had the capability, to create thousands of, hundreds to thousands of these digital twins, the copies of reality in cyberspace, with very accurate physics, extremely accurate physics. It's very difficult to model many varieties of societal situations, some of which we conceived, but a lot of which came from demand from the government, from the companies, etc. So we work with Toyota to work on, because the taxi cabs, so they're worried about taxi drivers being affected. The Ministry of Education, they were worried about bringing kids back to school. There was a general concern about restaurants, because people have to take off their masks. How do we prevent transmission in restaurants, et cetera, et cetera, et cetera. So we created all these digital situations, digital twins, and also the various mitigation plans to reduce the transmission. We can also calculate the risks accurately. And then as soon as we got the results, it was reported all over the news, all over TV, all endorsed by our ministers, by politicians. And that's how Japan became one of the countries that had the fewest cases of fatalities, despite that being most lenient in terms of lockdown. In fact, they simulate the effects of this using another supercomputing simulations of the economy. With these types of reduced or more stringent lockdown, more lenient lockdown, what would be the effect on the economy? And we estimated that we saved trillions of yens, or multi-tens of trillions of Korean won, in terms of the downturn, because of the fact that we didn't totally lock down the society. So, these, and also we advanced science, not only by simulating the exterior, but made scientific advances by simulating all the way from the lungs, transmitting through the air, being inhaled, and infecting the other person. So the entire process of infection from one person to the other, including your body internals and how the cells behave, were modeled using these technologies. Okay? So these are sort of advances that big supercomputers can make, which previously the scientists weren't able to do. And these kinds of innovations are what's expected, not only with simulations, but with AI, now in the mix of tools that the scientists can use. So it's not just about getting a chatbot working, it's to solve these types of very hard problems. Okay? Another is climate and weather. So we have this humongous radar, state-of-the-art radar, which can scan hundreds of channels at the same time. So we created, we have a very accurate weather simulation, but allow this combination of this real-time data, which is like multi-gigabits or terabyte per second incoming data from the radar, most advanced radar. We would combine it with this real-world simulation of Fugaku. This is called data assimilation. And then once we correct the simulation, we would multicast the result onto a smartphone. So people will get real-time account of the weather 30 minutes ahead with very fine resolution. So where you're standing, you get a warning. Oh, you're going to get a downpour in 30 minutes. But if you move away a kilometer away, you'll be safe. Okay? So you can get results like that. Of course, this involves very complicated, very difficult simulation. So we use about 1/10 of Fugaku, but continuously using about almost 10,000 nodes of Fugaku, but doing this continuous integration of data, combining with a multi-petoscale simulation, and then getting results out, and doing this at 30-second intervals. Okay, so this is what kind of a power of supercomputing can bring. In fact, we can even design new societal structures. So we can do a what-if experiment. A what if, okay, so given that these radars, experimental radars are very important, very effective, how many do we need? If we place them all around the country or all around the globe, where are the locations do we need to put them? So then we can, again, virtualize these radars and then place them and run virtual experiments and optimize the placement of these radars, because these radars are very expensive. Right? So, and this is a result of putting this in Kyushu. You can see a bit of Korea up there, right up there. But this is Kyushu. And so, you know, this is, so this is where the optimal radar location would be, okay? Assuming that we can put more of these radars in place. So this previous experiment was done with the real radar, but this is a virtualized radar. We can put, you know, we can put everywhere. So we did an analysis of how much economical effect these would have. The big supercomputer like Fugaku has, which costs like $1 billion to build. But the professional consulting firm came up with a number saying, you know, it's worth 60 to 80 times the it's worth. So hundreds, tens, so up to 100 to 135 billion US dollars. Okay? A single machine can bring to the economy. Okay? So what about AI? Well, so we have this computing, and we do the science of computing. We also do science by computing. Okay? What about science of AI? Which, you know, a lot of people do AI as a scientific discipline of study. But what if we do the science by AI? Okay? Same with quantum, but I'll skip the quantum stuff today. So we have now a new project, putting all these scientific capabilities we have and AI capability we have by applying it to science. Then what kind of effect? What kind of machine do we need? What kind of effect? So so of course, you know, AI can be used to, for example, large-scale observations, but more importantly, there can be generative AI, like there was the last talk of the award session. And these foundation models, and also the variant with the surrogate models, surrogate models will replace simulations to speed it up or refine this resolution. Foundation models used generally as models for generating. They can generate substances, as we saw in the last talk. We can also develop code. It can control and design and control experiments. Ultimately, we believe we can create AGI scientists, not in the manner that Yoshio Bengio mentioned. This is not the scientist for AI. This is scientists that are driven virtually. These are virtual scientists driven by AI to replace some of the functions that human scientists conduct, to make more advances, not to put scientists out of their jobs, but to enhance our scientific capabilities. In fact, I'll skip this, and this is, but one thing I must say is this is slightly different from your traditional AI. Because in traditional AI, a lot of people focus on training, and a lot of people focus on existing data sets. Our challenge is we'll work with scientific data. We have to make scientific discoveries. That's how we're judged, not on getting a better model, but making better discoveries. So there'll be a lot of focus on inference, not just on training. Okay? And also trustworthiness, well, it's important, as Benjo mentioned. It's even more important for science, because a hallucination under control, it may be able to destroy the human society, but at the end of the day, if you have a hallucination right now, you can say, well, I got this wrong info. You can throw it away. But in science, getting a wrong info is critical. It can destroy entire research, right? So, but on the other hand, because we have a model, we can have very good handle on getting to the right AI model based on the physical model. And we can automate the process of refining the AI model automatically rather than relying on human intervention. So we're working to really scale AI to tens of thousands of nodes on Fugaku. And there are many instances. I'm kind of running out of time, so quickly we can use in fact, all the science teams, practically all the science teams we have in the application space are doing some sort of science. So despite the fact that the MIT team was doing a great job, practically all the capable computational scientists in various application science space, if you think they're not doing AI, you're a complete mistake. In fact, all of them are very capable applied math, science, compute people. So there's very little exception that all of them are looking at AI as additional means to advance their science. And this is one area where we have one team at University of Tokyo to achieve 25 times speed up to achieve essentially 10 exaflop performance on the earthquake simulation to shake the entire city, okay, and get a very accurate result. AI is being used for design optimization combined with very accurate CFD to design new breed of cars that are not only aerodynamically efficient and also stable, but also look good. So aesthetics, things like aesthetics, being built into the AI, along with other physical parameters. And they'll be simulated for efficiency of CFD, but also aesthetics will come into play. So this automates the process of designing automobiles, which a single car designer can, in their entire career, they can only do maybe like 5,000 instances of car designs. A supercomputer coupling simulations, AI, generative AI design, on these big machines can do 5,000 design in a week, in 1 week. So that will greatly enhance the ability to do this, and to design, to do manufacturing. So, and in terms of these big machines, we need to be able to train these, do inference. So the combined team within Japan, also in the US, and also Fujitsu, trying to scale these training and also inference to tens of thousands of nodes. And also, we're trying to come up with, I'm sorry for the Japanese, but trying to come up with a scientific loop of creating these foundational models or pre-trained models, fine-tuning them, but automating the process, not having human intervention, by combining simulations, reinforcement learning, and instrumentation experiments. So this is the big science, AI for science work that will be just starting at RIKEN. So if you're interested in working with us, let me know. We're recruiting, especially if we get PhD. If you like Japan, please come and work with us. And we're putting all these in reports. We're trying to write out the report, AI for science, so AI roadmap. We already have a computational science roadmap. We've got more than 100 volunteers to enhance the roadmap. What can AI, high-end AI, do to impact science? So we already did this for computational science in general, in simulations, but enhancing a report with more than 100 volunteers, authors, to come up with a case for using AI for science, to advance science. And this report, the first draft of the report, will come out in March. Okay? And we're also trying to build new machines. Finally, so that's with our existing machines. And we will enhance our existing machine with training and inference capability. So you combine what will likely be a GPU cluster with Fugaku. Fugaku is pretty good in inference, but training, we need some additional power in training. Also, with some with inference, so we're adding a mid-sized GPU machine, maybe several thousand GPUs, a mid-sized machine like that. But our next generation machine in planning, which will come up in 2029-30, we are hoping, we are starting to design right now, along with not only like Fujitsu, but companies like NVIDIA or Intel or AMD, HPE, ARM, and maybe with Samsung, we'll see, in achieving the next breakthrough in machine performance and software algorithms to drive the next generation science combining simulation, AI, and this whole technology permeating to rest of the ecosystem. Okay? So working on this next system, we've already started to work on the next system to come online in 2029. Again, if you're interested, please come. You can talk to me or talk to any of our PIs. And but the whole one final slide is that most of the apps are bandwidth bound, not compute. So flops doesn't matter. With an analysis, this is the roofline curve. Most of the applications are bandwidth bound. But we've got a big challenge because we try to increase bandwidth by a factor of 10 or 20 in the system, memory bandwidth. We need to reduce the energy down to minuscule levels, like 0.2 picojoules per bit. That's a huge challenge. And when you think about AI, oops, I'm sorry. Okay, I didn't have the slide for that, I'm sorry. When you think about AI, not even HBM will cut it, but the situation is almost exactly the same for AI inference. And AI inference is 10 times a bigger market than AI training. Okay, so if you want to have a real AI impact the world, you got to work on the inference. But inference by nature, just like many HPC applications, is a memory bandwidth bound, not compute bound. So we're putting a lot of emphasis on the next machines. We're thinking about various types of architectures. But our foremost technological concern is how to achieve high bandwidth, not compute, while keeping our energy low. Okay? So that's the end of my talk. Again, if you're interested, please come talk to me or contact any of our contacts. And thank you very much. It's been an honor. Thank you.
Thank you very much, Mr. Satoshi Matsuoka, for the valuable presentation. Now, ladies and gentlemen, we'll dive right into the first session. I'd like to invite Mr. Zaid Kahn from Microsoft, who will be presenting on meeting the memory challenge, AI's impact on data centers. Please greet him with a big round of applause.
Thank you, everyone. It's really a great honor to be here. I would like to thank my esteemed friends and colleagues from Samsung for inviting me. First time in Korea, too. Food is great. So, I'm Vice President of Cloud AI and Advanced Systems. What that means is I'm responsible for all of Azure's hardware development. So every piece of hardware that goes on Azure is developed by my engineering team. So I'm responsible all the way from supercomputer development to general compute, memory, storage systems, and the whole thing, right? And of course, AI is the thing, so there's a lot of focus on that. And I also am involved in our custom system development because AI is all about hardware and software co-design. Okay. Where we are in AI today, right, is really an incredible stage, right? It's as we look back, the advent of AI is not just another, next piece of technology. It is a paradigm shift, right? What it means is that we haven't seen something like this since, the invention of the PC or, when the internet was formed or when mobile was formed. In fact, I don't know if maybe AI is much bigger than all of them combined. We just don't know, right? The journey is so incredible, and the paradigm shift is so massive, right? So I want to talk about how embracing platform and tech paradigm shifts have been the foundation to success. Technological advancements disrupt industries and redefine companies. Choosing to be at the forefront of change is not a choice, it is imperative, right? When we anticipate paradigm shifts and embrace opportunities to innovate and break new ground, we deliver solutions that transform the way our customers operate. So conversely, when we fail, we do so when we face the possibility of extinction, right? And under-delivering on our mission and to our customers. Every major platform shift that you see here, it deeply shakes up the technology chessboard, and there will be winners and there will be losers, right? Winners leverage first-mover advantage and deliver large economic value, while others face uphill battles and can risk irrelevance, right? I don't know why it's doing that. Oh, I went the wrong way. Sorry about that. Still trying to get used to this clicker. All right. So the buzz around AI is super hard to miss, right? You cannot get on a conversation with your friends, your family, getting on the bus or the train without someone talking about AI, right? It's hard to miss. Actually, Satya Nadella has even indicated AI has the potential to be a bigger disruptor than the innovation of the internet, as I said, or anything else, and its presence is becoming more relevant than ever. So a recent study found that more than 75% of leaders today believe that AI will give their organization a competitive edge. And now they're asking themselves one key question: how can my company seize the full potential of AI? So, with Microsoft Cloud, before I get into this graph, we help our customers power their AI transformation in different ways, right? First is we build AI capabilities into the Microsoft Cloud solutions. Customers are already using today, helping everyone to be more productive, more creative, more efficient, more innovative. This is what we mean when we talk about Copilot for every Microsoft Cloud experience. See, at Microsoft, we are very passionate about making sure that AI is helping everybody's lives, right? Is helping them be more productive, helping them to do the tasks that are mundane or something that you can just move on as a society and focus on for the next advancement, right? Oops, I went back there. So we also are making it easy for any organization to co-innovate with our partner, build their own intelligent apps and Copilot solutions in the same stack that Microsoft used to build our own Copilots. Let me see if I'm doing this one right. Oops, I'll go back again. Sorry. Oh, my note is off. Can I go to the next one? Can I go to the next one? Next one, I think. Okay. All right. So let's talk about this graph now, right? The problem statement. Now let's talk about memory. So memory has largely been flat, and actually, sadly, continues to be flat, right? So is networking, not just memory. But as my esteemed colleague before was saying, network and memory are really the big problems in supercomputers today, building supercomputers today, right? If you look at it, training has grown by 750x. Just imagine that for a moment. In a year, 750x, right? And it's growing by exponential factors. Computationally, sort of the underlying building blocks such as networks, memory, internet, just not keeping up enough, right? You can see that it's really fast. Look at the order of magnitude, right? 750x in 2 years, sorry, not 1 year, as I said before. Memory, 1.6 in 2 years, right? Interconnect bandwidth, 1.4 over 2 years, right? So when you look at large cluster supercomputer deployments, the size of the language models do not fit in, obviously, anymore in a single 4-node or 8-node GPU. It doesn't even fit in a rack. It actually has to span across multiple racks, right? So we have the model sizes outpaced, not only just memory and network interconnect, but also the system aspect of it, right? Like we cannot build and scale systems fast enough and keep up with it, right? For decades, our industry has been very comfortable, right? They've just been focused on incremental progress. But as you can see with AI, it is not an incremental progress. It is a massive shift, right? So the speed at which AI models can evolve, produce outcomes is limited by how quickly we can evolve a supercomputing architecture and hardware to meet this new challenge. This is a very difficult problem to solve. Sorry about that again. Okay. So what do you have to really think about when you're designing for AI, right? You have to innovate new system architecture, right? You really have to think everything from ground up, not sort of the very traditional way. Your rack architecture, how your system fits inside the rack, how you do your cabling, all of this has to be completely rethought, right? You have to think about advancing packaging for new memory types, right? That's a very, very important aspect of it, right? So designing is not just innovate, but disrupt in this domain, right? So as I mentioned before, right, there's a lot of computational power that is needed. We've got a lot of powerful GPUs, new types of processors, and novel architectures that deliver cutting-edge performance with high-density packaging and smaller physical footprint. So to manage this massive training data sets, we need to rely on like 3D advanced packaging and use of higher bandwidth memory modules while balancing trade-offs for power and cooling. You have to also rethink how you do your networks, right? Do you do everything under a T0 domain? You want to keep all your traffic within that. In inference, you typically want to do that. In training, it's not always possible. The other thing that we cannot lose sight of is advanced cooling technology. TDP is just going higher and higher every year. We are probably by this time next year, definitely in the 1200 kW per chip TDP. And if you stack that across, up and down your rack, you absolutely need liquid cooling. You have to even start thinking about liquid cooling at the component level, right? So a lot of these new designs are just imperative, right? So let's talk about memory implications in a little bit more depth, right? So GPT-4 is over 1.75 trillion parameters. As you can see the graph, it's really way up there, right? And GPT-3 was just 175 billion. So it's a massive shift, right? And so the number of parameter growth is just exponential. You can't even say doubles, right? And model performance is dependent on the ability to process large amounts of data quickly, right? So let's pause on that for a little moment. So what that really means is when you talk to a person who is working on the model, if you just step across and say, hey, what do you need today? They're just going to tell you one thing. I want more HBM. I want more capacity, and I want a lot of bandwidth to push through it, right? So, and then the third thing they talk about is latency. And if I'm doing inference, I want my whole end-to-end system to be low latency as possible. So when we think about how do we build our systems that specifically around how memory relates to it, we think about capacity, bandwidth, and latency, right? Because those are the three big questions that keep asking. And when I go and talk to folks like you in the industry, I keep saying the same message, right? Developers want more capacity, more bandwidth, and more latency because it's all about weights. The closeness to the GPU and memory is where all the magic happens, right? And of course, there's a lot of opportunity out there for second-tier memory and other things you can do. But at the end of the day, the weights are all computed right. On HBM is the key aspect of it, and so we need to continuously evolve the HBM landscape, a lot faster. So another way of kind of looking at this is a message I wanted to sort of like portray is that as hardware scales, reliability and cost become critical. Now, I'll share with you something. Like one thing that's actually advantageous to AI training and inference is that the developers have got this thing of concept of checkpointing. So unlike general purpose, computation, when you had your stack in the computer in the rack, if you had a reliability issue or if you wanted to do something, you would lose data, right? The state machine was very, very important. Well, with checkpointing, the advantage of that is that things can fail, but at least they know that I can go and checkpoint to my last hour and do that. However, at very, very large scale, at the scales we operate, the reliability starts to impact capacity. And that's a big, big issue for us, right? So if I have hundreds of thousands of GPUs on my fleet, and I have 5% that is not there because of reliability, that is a very big number for me, right? So the capacity sort of really becomes important, right? So I would recommend that reliability of memory, is something that needs to be relooked at. Your RAS, your telemetry, all of these kind of things, right? And the other one is, cost is very, very important. The cost of HBM is 3 to 4x, right? And at scale, we deeply care about how performance per dollar, performance per watt operate. Those are our standard metrics. So at some point, when we take large models and we want to see, hey, is this training cost effective, right? So it will matter. So the cost of HBM over time as technology goes needs to come down, right? So a lot of people had asked me about storage, what does storage have to do with AI? So I just wanted to give, an overview. Like the storage story is not that sexy. It's not something like refined, right? Storage is largely, I would say that could be flat, but local GPU and SSDs need to keep up with the compute capabilities, right? So like 4 terabyte, 8 terabyte, 16 terabyte capacity. You need Gen 4, Gen 5, 6 performance, from your PCI stuff. You need use case types of random, sequential, those kind of things, right? So you need to keep up with the capabilities. Your SSDs need to be improving at the petabyte, scale of things. And then, the role that HDD plays is basically just holding large sets of training data, right, and archiving results. So it's not a big problem like HBM, but there is a play there. So I wanted to make sure I talked a little bit about it. The thing that, my last couple of slides here, I want to talk about sort of like a call to action, right? And I've been spending a lot of time thinking about, well, memory is just not keeping fast enough. We need to look at something very different. We just can't look at stacking a bunch of HBMs on the die, right? We just can't just stack up the problem. So what I really wanted to put out there is that we need to start looking at silicon photonics in a very serious way. We need to bring in silicon photonics, which I know is a hard problem, but we need to really bring that in because the bandwidth problem around that is only going to be addressed by something like that. People talk about Moore's law. I say, well, Moore's law is there, but there's also a Moore's law of copper, right? So to me, that's just the Moore's law of copper problem, right? And so, there's good work being done I've seen on photonics interposer, enabling off-package expansion and access to point of compute. So these kinds of technologies, I really think should be there. So innovation I just kind of want to leave before I go into Q&A, that the capability to scale in the memory space, in my opinion, is declining. And we need to do something about it. Current solutions to address challenges have their limitations, right? With AI workloads shifting more and more pressure on size, performance, capacity, and you need to also pay attention to TCO, as I was saying, perf per dollar, perf per watt. All of these are very, very important aspects we care about. Speed and bandwidth. As I've said before, these are, super important things that any AI model scientist is going to ask every time, you want something, when you ask, hey, what is it that you really want, right? So industry must innovate together to create radical scaling solutions to address the future. The solutions need to be groundbreaking to pace up with the rapid innovation. Thank you. I'm happy to take questions if people want, if there's time for that. If not, then I'm happy to talk in the hallways on this.
Thank you, Mr. Zaid Kahn, for the wonderful presentation. We would like to take some questions from the floor if there are any.
Yep.
질문 있으신 분들은 손을 들어주시면 저희가 마이크 전달하도록 하겠습니다.
Thank you for the great talk. I'm happy to hear your presentation. So today, most people usually focus on the memory bandwidth in terms of DRAM, but I wonder what might be the challenges we are facing from the perspective of storage systems such as SSD. So do you have met any challenges about storage system when you're building AI systems?
I think, as I said, right, we haven't really experienced any problems, and we don't anticipate, because to me, it's all about local storage, right? So the thing about when you build these systems is that your compute, because SSDs are attached to the compute. So the compute is think of it like an accountant now, right? If you think about like your stack, you have one compute and then you have like 4 to 8 GPUs, right? So what your compute is doing is just doing the processing of passing information for your training, like your tokens and all of these things, right? And so it is really not stressing it that much. It's just passing information. All the heavy work is being done on the HBM and the GPU, yeah.
Can processing in memory be a breakthrough for the improved interconnection bandwidth in the future?
Great question. I've been having some discussions on that actually not long ago. So processing in memory, I think, has good potential. It is definitely, the von Neumann bottleneck is a real problem now, right? Like, before, we kind of knew about it. Now it's a really big problem. So we can't, even if we do like second tier memory, you still are going to be thrashing a lot. And yes, we don't want to be moving data back and forth, right? So I think I think I love that technology. I think it's good. It's just something that I would recommend you keep pushing, because the problem is not so much in the hardware, it's in the software, right? You have to make sure that that your processing in memory technology can be used by a developer in the most easiest way without adding a lot of software complexity on top of it to manage it. That's where the harder part is. I think, keep persisting that area if you're working on it. I think it's great. We need technologies like that to bring, to solve the hard problems in this space. So great question. Thank you. Yeah.
Thank you for the question and the answer. Due to time constraints, I believe that we will have to wrap up the Q&A session
Thank you.
now. Thank you very much. 감사합니다. Next, ladies and gentlemen, I'd like to invite Mr. Masato Motomura from Tokyo Institute of Technology, and he will be focusing on AI computing, tackling the explosions of data to process and decision to make. Please welcome him with a big round of applause.
Okay. Thank you very much for this very kind invitation, and very happy to be here and happy to give some presentation. So, okay, the slide here? Yes. The title is AI Computing, Tackling the Explosions of Data to Process and Decision to Make. The latter half part is a kind of, a new kind of phrase, I believe. So, just a brief introduction of myself. I was the researcher at NEC Research Labs, and did some work on parallel processors, near memory computing, and invented and productized dynamically reconfigurable processor called DLP. It was for virtualizing hardware with reconfigurable data path. And I believe it's a little bit similar in concept to Samsung reconfigurable processor, SLP, and DLP and SLP is very similar, right? And so I'm not sure, how SLP is used in Samsung, but for this DLP, it has been commercially successful. Now, series of microprocessor products from Renesas is integrating this DLP for embedded market. And there will be some presentation from Renesas on new so-called DLP AI at the coming ISS's 2024. Okay, then I have moved to Hokkaido University and then go to Tokyo Tech. Now I belong there, and I'm organizing a so-called Artificial Intelligence Computing Research Unit, ARTIC. And Dr. Jahun Yu at Samsung, he's there, had been a member until February 2023. So he kind of invited me this time, and I'm missing him so much. I'm kind of missing so much. Samsung took him away from me. So I have something to say about that. But anyway, so my office is in the Suzukake-dai campus, which is the main campus of Tokyo Tech is Okayama, and the Suzukake-dai campus is a kind of a little bit far distance from downtown Tokyo. But if you're interested, please plan to visit our office and plan to visit Suzukake-dai campus. All right. So this is the kind of background of the talk, and I think this issue has been covered by all these speakers already. AI technology is now omnipresent in our society, and a serious concern is its energy consumption and environmental impact. As it has been said, training ChatGPT consumes hundreds of years of ordinary families' electricity, so it's a huge amount of electricity required. So AI computing should become more energy conscious. That's kind of my standpoint. So, what is AI computing? This is an observation from my point of view. I believe it is all about how to handle large volume input and output to computers. So for the input side, so explosion of data has been, has been a keyword around for, decade or something. And for the output side, explosion of solutions is getting a big issue. For the input side, technology like traditional machine learning, deep neural nets, and/or reservoir computing has been under research. And for the solution side or output side, discrete optimization, annealing computation, and graph type of processing is being researched for solving that kind of problem. And these technologies will kind of summing up for doing classification, detection, recognizing, predicting, and decision making. So that's my point here in this slide. Okay, so not only the the balance between input and output, I believe there are some common background between the deep neural nets for the input side and annealing computation for the output side. So that is driven by energy minimization principle. So for the DNN side, it's like like in the Jim Keller's presentation this morning. So it's a kind of graph structure, and where data flow is mapped. And for the annealing computation, annealing is kind of the pseudo-binary operators that constitute energy function. Okay, I don't know how to point, but so energy function, like called Hamiltonian, and the annealing computation is done like finding the local minimum of the energy surface. So those kind of energy functions has been known to have lots of local minimums. And as I mentioned, for the annealing computation, it traverses the energy surface and find a minimum. For the DNNs, its story is a little bit different for training and inference, but for training, it is to design the energy function by SGD or backpropagation. And for the inference, they're traversing the energy surface and find minimum. It's a little bit similar to annealing side, even though it's different, discrete or non-discrete problem. But something common they have is that energy minimization principle. Our goal as a researcher is to establish common architectural ground for specifically for these two research domains, or in general, more in the machine learning and discrete optimization problems. Okay, so for that based on that kind of motivations, we have been working on various AI chips during past years. In this slide, blue colors are DNN chips, and green colors are annealing chips. We've done this research work and presented at ISCC, VLSI Symposium, Hot Chips, those kind of top conferences. And as an academic player, the process technology is very old. So we have to put our efforts on establishing some new idea and prototyping with using the old technology. So today I would like to cover just two of them. First one is the fixed random weight DNN inference accelerator, and that has been published at the ICCC 2020. So this work is based on so-called lottery ticket hypothesis. I'm not sure how much % of this audience knows it, but it's very important and very interesting hypothesis, which basically claims that there is an existence of subnetworks in the original dense train network, with which it's very sparse and random, which can achieve equivalent inference accuracy. So this was an hypothesis. the famous paper, iClear 2019. And following to that, there has been a proposal for hidden network, or these days it is known as strong lottery ticket theory. Now hypothesis became theory after that. So what it says is that there is an algorithm to find a supermask for subnetwork by kind of pruning from the original network. But what's different from the ordinary pruning is that the initial random weights does not change. So you can keep that initial random weights. So training is not for the weight values. Weight values stay the same again, but you train the supermask, which is to kind of cutting off the dense neural network, which connections to utilized. So again, no update of the weights. And I do not have time to go into detail, but in this theory, the training is done not for the weight, but scores. Scores is kind of latent weight or something that's hidden behind the network. Okay, so again, hidden neural network, HNN, utilizes fixed random weights. So, and it is fixed at initial random numbers. So that means weights are no longer variables, but are random constants. That is a very big a differentiation from the ordinary neural network. And also, it has been found out, it's been known that binary weights, -1 and +1, show better accuracy in this HNN context compared with the multi-bit weights. So we can, in some sense, we can get some binary neural network with fixed random weights and can achieve a good inference accuracy. So that's very good news. But HNN needs a supermask, as I mentioned. Supermask is a kind of binary 0-1 information, and that is for selecting connections, which connection to use. That is called supermask. And supermask is, as in this figure, kind of overlaid on the weight, and you can take the AND, so that the selected weights are used for the HNN inference. And this is the downside is that conventional neural networks do not need supermask. But supermask can also provide the trade-off between accuracy and sparsity. It doesn't work. Okay, so this is the you can see the graph over there, and the horizontal axis is top K% of weights. How much % of weights are used from the original random neural network, and the peak is around 30%. 30% top K. So you can use 30% of the original neural network, and then can achieve quite equivalent level of accuracy. And you can see that there is a curve of, there is a curve there going up to top 30% or something, and then going down. So our work based on strong lottery ticket theory, or HNN, was the first HNN inference chip called Hiddenite. That we named that Hiddenite from the concept of finding out some precious thing from the random neural network. In this work, we have designed 3 key technologies. First one is on-chip weight generation. As I mentioned, the weights are now random constant. So the key point is that you don't have to remember the weight. You don't have to memorize the weight, because you can generate those numbers. So as people are saying, memory bandwidth or memory access is a source of energy consumption, but you can reduce half of that basically by using this type of technology because the weight can be generated. And in addition to that, we need supermask, but that supermask is 0-1 information, and it's kind of sparse. So you can compress the supermask to reduce the memory requirement. And so we have also designed high-density 4D parallel processor for handling the inference, HNN inference. So this is the overall chip architecture. On the top side, there is a supermask expansion unit. So the encoded or compressed supermask is loaded from the outside and then expanded and used. And there is a 4DP tensor with 4,000 Ps. I will cover that shortly. And most importantly, in the bottom, we have weight generation unit for the generating weights. This is the quick sketch of the 4DP tensor. It's a kind of ordinary parallel processing elements array for handling activations on weights. But here we have supermask. So weights are coming from the bottom, and supermask are coming from the top, and that is they are taken end, and then activations are handled accordingly. So since the weights are binary random numbers, and the supermask is binary also, so it becomes very compact database. And we have done further for the reducing memory access by generating weights by hashing. As I mentioned, the weight can be generated by random number generator, but you may have to memorize sheet for the random generation. But here in this work, we have found out that the network information, like number of channels, channel numbers or layer numbers, such kind of information that should be used for handling neural network, can be used for hashing. Sheets for hashing, because since they are required anyway, we can virtually reduce the information for generating weights to 0. So everything, you don't have to memorize. You have to memorize nothing. So hashed Cs eliminate the need to store weights without accuracy degradation. So this has been the new finding in this work. And since we've done the kind of memory reduction techniques, total external memory access has been reduced quite much. This is for ResNet 50 ImageNet top 10% model. Without the so it's like in total 93.4%, the red color, memory reduction. So everybody kind of designs neural network accelerators and talks about the power efficiency, but often cases the data path power consumption is much lower than memory access power consumption, and the key is, generally speaking, you have to reduce memory access, and memory access is the most important thing in that sense. And this work focused on that by utilizing the HNN concept. And so if the model is very small, if you cannot achieve good accuracy, that is meaningless. But here we have found out the for the ResNet 50 and VGG 16 for the ImageNet and C500. So our improved version of HNN or strong lottery ticket has shown the quite compatible accuracies compared with the traditional binary or ternary neural networks. Okay, so this is the chip photo. So as I mentioned, we have fabricated chip with using TSMC 40 nanometer, and this is the measure results. And tops per watt is like 18.2 to 16.2 tops per watt. It's a kind of called sparse tops watt. It becomes better. The neural networks is sparser. All right. So what Hiddenite has achieved, Hiddenite is the first HNN inference chip. It drastically reduces external memory access, which is the most important, as I mentioned, by on-chip model construction, which is on-chip weight generation and on-chip supermask expansion. It can achieve state-of-the-art accuracy relative to model size by score distillation, which I didn't cover, but SOTA level and computation efficiency. And not only the architecture and chip implementation, we have published some algorithm work at ICML 2020, which was a multi-coded supermask and a little variation of this supermask training. So I would like to insist to do some architectural work, not only the microarchitectural circuits, but also the algorithm side research is quite important. So the combinations of those algorithms to architectures, will differentiate your work. That's my belief. Okay, I think I would like to go to the next topic, which is metamorphic annealing engine for fully connected models. I was presented at this year's ICCC. So combinatorial optimization, for decision to make appears everywhere. And the famous traveling salesman problem, when the number of cities increases, the combination explodes, and it becomes very difficult to decide. So it's NP hard. And the annealing is the computation optimization based on the Ising models. It is inspired by solid-state physics. And combinatory optimization problem is kind of mapped onto the Ising spin structure, and by introducing pseudo-binary operators like which is called spin. But spin is not a magnetic spin. It's just binary operators, -1 or +1. And so that you can define some energy space, as I mentioned earlier. And the annealing process is to find out the local minimum or global minimum of that annealing energy surface. And the solution found out is kind of remapped again to the actual solution for your specific problem. So this is how annealing works. And so the annealing computation has been famous because quantum annealing processors has been taking foundation on this kind of algorithms. And there, simulated annealing has been the one key technology. But we've analyzed that simulated annealing is way too slow, because the spin update or binary operator updates is basically serial. You have to decide one spin to go up or go down, and then taking into that account and do the next. So as appeared in the left side of this slide, it's basically very serial. And our proposal, which was ICC 2020, one work before that, was to do it in parallel by stochastic cellular automata annealing. So kind of replacing Ising model to the several automata where you have local rule, and that local rule can be applied in parallel. That was the kind of the key differentiation of this work. And it's very fast because SGA can realize order n times faster because it is in parallel. But after that, we're working on SCA, which was the ICC 2020 paper, but we saw some challenges. So challenges, first challenge is limited flexibility. So we've done a parallel spin update, but for some problem, it's kind of overkill, too fast, and the solution does not become stable for some problems. That's what we found after that work. And the next issue was the limited scalability. The problem size gets bigger for combinatorial optimization, so you may need to tie up multiple chips for handling larger problems. So that's the kind of the issues that we've found. And here in this work at the ICC 2023 work, we've done a couple of innovations. First one is RPA, ratio-controlled parallel annealing, that I will introduce a little bit. And the second thing is metamorphic annealing architectures, where we can apply different set of algorithms for annealing depending on which type of program to solve. And third point is the multi-chip extension. And as a fourth item, with the chip implementation. Oh, sorry. So, again, this is the algorithm architecture, microarchitecture, circuits type of the work, holistic kind of work for doing this. Okay, so this is a comparison of annealing policies, which is kind of illustrating for you to understand easily. In the simulated annealing, you have various spins. Red is going directing upper direction, and yellow is lower direction. And for the simulated annealing, you will randomly select one of them and judge whether to flip or not. So that is how SA works. And Fujitsu had developed their own digital annealing processor, which is a kind of the improvement over SA for speeding up something. And our proposal was SCA, and this time RPA. SCA, again, is to do it in parallel. And RPA, we apply some probability, which is called epsilon, for kind of gradually controlling the parallel spin flips by this new hyperparameter. But anyway, SCA and RPA are parallel spin update architectures, and which is basically very much faster than SA or DA. So, but we have, RPA, new proposal, but we did not, we were not able to solely rely on our new proposal, because when we analyze the problem space, this is a kind of the very toy example, but toy example itself had shown us quite a variety of characteristics. On the right-hand side, the horizontal axis is the positive coupling ratio, and the vertical axis is the negative coupling ratio. And overall, our proposed RPA is better in the red region, but when you go to the very negative coupling region, DA becomes better. So this is the kind of analysis we've done, and this this finding has been very new. So this motivated us to do the metamorphic annealing. So change the annealing policies even in the middle of the annealing to converge the annealing process very fast. So I think I'm running out of time. I'm sorry about that. But so let me cover the rest of my presentation quickly. So this has been the Amorphica metamorphic annealing architecture, which is very near memory type of processing. This gray region is memory, and our logic is very simple, and it's sitting just nearby memories for doing parallel spin updates. So it is again near memory, fully spin parallel architecture, and importantly, and interestingly, it is very close to what binary neural network inference chip looks. So it's a kind of there seems to be exists a common architecture ground for annealing and quantized neural networks. So this is the chip summary. Again, TSMC 40 nanometer. And when you compare to GPU, the energy efficiency, since it is parallel and kind of customized architecture, and the bit size is quite reduced, it achieves the 30K times more energy efficiency. Okay, so I'd like to wrap up this talk. Okay, so we've covered the two of our work. One was the DNN, another one was annealing, and which is related to input of computers and output of computers. And I believe they all feature a reduced bit width, near memory, and element-wise parallel reconfigurable computing. And I believe key message here is this type of AI computing architectures will play key roles in near future SoCs. And so this is the final slide. SoCs for the smart future will include domain-specific cores like DNN engines, annealing engines, and tree list graph engines, and sparse engines. So that is not application-specific, but domain-specific cores, and that kind of domains is expanding. And they are on some common architectural foundation. And as we covered, we have done the test chip architecture proposal and test chip implementation for DNN engines and annealing engines. And we are also working on the tree list graph engines and the sparse engines, and with using FPGA prototype, and we'll publish the last version at the ASP DAC at Incheon next year. Okay, so we are working on new engines with more ideas. Okay, thank you very much for the kind invitation, and maybe I ran out of time for taking questions, but I can answer the questions later maybe. Thank you.
Thank you very much, Mr. Masato Motomura, for your wonderful presentation. As he's mentioned, due to time constraints, I'm afraid we won't be able to take any questions, but you may feel free to ask him any questions later after the event is concluded. Then, ladies and gentlemen, yes, can we give him another big round of applause? Thank you very much. 큰 박수 한 번만 더 부탁드리겠습니다. 감사합니다. Then, ladies and gentlemen, we are now left with only one last presentation for the first session. As our last presenter, we have Professor Joo-Young Kim from KAIST, whose presentation is titled Latency Processing Unit for Acceleration of LLM Inference. Please welcome him with a big round of applause.
All right. Hello, everyone. Can you hear me well? Okay. So my name is Joo-Young Kim. I'm a professor at KAIST, but today I came here as the CEO of HyperAccel. HyperAccel is the startup company that I co-founded with my fellow students. And at HyperAccel, we build AI processor and solver solutions for generative AI, making it faster and more sustainable. I'm deeply honored to be invited here in Samsung AI Forum, and I'm very excited to present about our work on latency processing unit. So here's the outline. So generative AI is the latest AI technology that can generate human-readable text or image. For example, if you give an interesting instruction of, what if Picasso painted Elon Musk? Then you can actually get the answer from AI model as shown on the right. That is very impressive result. And this actually shows the creativity that we once believed only human can do. This is why this generative AI is so impactful and transformative. So this generative AI is based on a model, new model called Transformer, released by Google in 2017. Since then, all the big tech companies, Microsoft, Google, Meta, are working on these large generative AI models. And of course, we have OpenAI, who is the creator of the very famous GPT models. And since all of these models are based on human language, these are often called large language model or LLM. As we all experience with the case of ChatGPT, these LLMs are now the mainstream of the AI, and it changes the whole AI landscape as well as our lives. To run this large AI model, we are heavily rely on GPU platforms. But as you all know, GPU server price is very high, around $200,000, and its cloud rate is also very high. So using GPU platforms in learning LLM inference has three major problems. The first is obviously the cost. It can be unsustainably high for inference services. Second is the speed to market. You have to wait for a long time to deployment because of the supply chain issue. Third is the domain expansion problem. Considering its size and the power consumption, it is hard to expand to various industry domains such as edge and mobile. To solve this problem, we provide low-cost, low-latency, and domain-optimized computing platform for emerging generative AI. So our motivation is simple. When you run LLM inference for generative AI services, currently we are using multiple GPUs. However, this costs a lot and this consumes a lot of power, hence not sustainable. So our proposal is to use specialized hardware optimized for generative AI so that we can reduce the cost and the power, so making it more sustainable to many other industries. So text generation is the fundamental and the most compelling task of the LLMs. It automatically generates human-readable text by language model. For example, if you give an input token, tokens of hello, my name, and the LLM gives you, is James Smith. Nice to meet you. What's your name? We also this in OpenAI's ChatGPT, Bard AI, and we can even apply this to other languages, including coding, programming languages. So Microsoft Copilot can help you on coding. So if you look at a little bit detail, text generation consists of the summarization and generation stages. The summarization stage handles the input side of the things. So it handles input tokens from the user and understands the context out of it and generates a single output token. On the other hand, generation stage, the language model sequentially produces output tokens. So the output of the summarization stage goes to the input of the generation stage and generates a single output. And how it generates multiple output tokens is that it needs to repeat this process again and again. So this auto-regressive read process of the LLM becomes the bottleneck of the entire system. And this is really memory bounded, memory bandwidth bounded application. So let's take a look at LLM computations. So the main operations includes token embedding that converts the input tokens into embedding vectors, and it goes through tens of decoder layers. And this decoder layer is composed of layer normalization, self-attention, residual, and feed-forward network. And the LLM head layer at the end converts the final embedding vector into the output token. And as I mentioned, the input of the generation stage is a single vector, and it produces single output vector. And you have to iterate this again and again to produce multiple output tokens. So if we consider training and the inference, for the training, we can actually have a batch of input samples. So even the generation stage becomes matrix-based, and it really becomes compute intensive. So the throughput-oriented machine, such as GPU, is the perfect fit for this. However, on the other hand, in the inference, which is related to all the AI services, you have to handle about small batch or even a single batch, single input. So all the process becomes really memory intensive, and we need latency oriented hardware for the real-time operation. Now, let me introduce our latency processing unit, or LPU. So LPU is the world's first hardware accelerator dedicated for LLM inference. So the most important hardware metric to run this LLM is the memory bandwidth. So our LPU is really designed to maximize this memory bandwidth utilization at the system level. To this end, we have streamlined memory access for the memory interface optimization. We have two types of execution engines. The first one is the streamlined execution engine, which is responsible for matrix vector operations such as self-attention and feed-forward network. And the next one is the vector execution engine that handles the vector operations such as normalization and residual and nonlinear functions. We have multi-bank register file-based local memory unit to produce fast access to intermediate values. And we also have instruction scheduling unit that controls the overall execution flow of LPU. The interesting thing here is we also embed P2P networking interface for data synchronization among multiple LPU devices. Now, let me explain about the microarchitecture of the LPU and how it operates. The first is the memory interface. The streamlined memory access unit is a specialized DMA that interconnects all the memory channels and guarantees to transfer data from the off-chip memory to on-chip memory at high bandwidth. It supports hardware-aware data mapping and tiling scheme so that it doesn't have to do any type of reshaping or reswitching at the runtime. So, and for transpose operation, it uses non-critical writing phase so that it can read the tiles at high speed at the next iteration. With these efforts, LPU can achieve up to 90% of memory bandwidth utilization during entire LLM inference operation. Our current LPU has 32 memory channels, so it reads 2 kilobytes of data every cycle. That amount of data are flown into the streamlined execution engine, which is the most powerful unit in LPU. The streamlined execution engine is parameterized to have L number of MAC trees, where each MAC tree can handle D number of vector elements in parallel. And this R&D number, of course, corresponds to the size, the width of, and height of the tile. So all the incoming data from the streamlined memory unit matches with the streamlined execution engine. And this streamlined execution engine is deeply pipelined, so it can process the incoming data without any stall, retaining that 90% of memory bandwidth utilization. And the vector execution engine responsible for vector operations can exchange the data with the streamlined execution engine through the local memory unit. And the instruction scheduling unit does out-of-order scheduling so that both engines can work together to improve the hardware utilization as well as reducing the entire latency. In addition, LPU is a programmable compute core optimized for the end-to-end LLM inference. It has 3 types of instruction sets, compute, memory, and network. And each instruction is very high level, like a SIS-type processor. So each instruction can handle such as layer normalization or matrix vector operation. So you can actually code a single GPT decoder layer with less than 30 lines of code, as you see here. And by repeating this again and again, you can map entire LLM model. Now, let's move on to our peer-to-peer network technology called Expandable Synchronization Link, or ESL. ESL is a highly expandable network technology that is devised for data synchronization among multiple LPUs with latency hiding. So since LLM has a big size, it cannot fit it into a single device. You have to partition it and distribute them across multiple devices. Since we partition each layer, each LPU ends up getting a partial result of the final output. And we have to share these partial results among all the LPUs to proceed to the next layer. So this is a all-to-all data communication and data synchronization. And how we do this effectively is like following. So what happens is that execution engine stores the final partial embedding on the outgoing buffer instead of the register file. And once the outgoing buffer gets a ready signal from neighbor LPUs, it sends the partial result right away. Likewise, the current LPU also gets the partial results from the neighbor LPUs and sorted to the register file. That's the number 2 and number 3 in this diagram. And more interestingly, the execution engine actually moved to the next part of the matrix processing so that the processing of the next iteration can happen with the communication of the current iteration so that we can effectively hide most of the communication overhead with this technology, except the very small latency at the end. So that is the core thing of the ESL. And to this end, we build a simple full duplex router embedded into our LPU. We also build software stack called HyperAccel to bridge LLMs, high-level LLMs, into multi-LPU system. So currently, we can support various LLMs, including OpenAI's GPT, Meta's OPT, and Llama 1 and 2, and their variations. The very first layer of the software stack is the model parallelization. This parallelization layer applies intra-layer parallelism for self-partition and feed-forward network. And the model mapper here generates the model binaries with finding optimal memory allocation and alignment. And the instruction generator generates the instructions for the partitioned model. and it applies parallel instruction chaining for further optimization for maximum latency reduction. After a few more optimizations, the device runtime and device driver loads the compiled model binaries and compiled instruction binaries to the multiple LPUs and drive them to run target model. That's how it happens. So finally, we build our LPU hardware and software platform using commercially available FPGA accelerator and built a server appliance. So this is our very first product called HyperAccel Orion. HyperAccel Orion is a Gen AI server, and we use 8 AMD FPGA accelerators in the system, in the 2U server, so that it can have 128 gigabyte of HBM with a total bandwidth of 3.7 terabyte per second. At the system level, we effectively use most of this bandwidth given by the hardware. And this server platform is really flexible, so we compare the result of this against a few GPU platforms using L4, A100, and H100. So this slide shows the model performance result of our HyperAccel Orion server. We use the OPT model from 1.3 billion to 66 billion. We use 8 LPU devices, and we fix the token size to 2048. For a 66 billion model, we got about 24 tokens per second. For 30 billion, we got 46 tokens per second. For 6.7 billion, we got 175 tokens per second. And for the smallest model, we got more than 500 tokens per second. So we get this really comparable result against compared with the GPU platform. And as I mentioned, our platform is really flexible so that we can map many different models and many different sizes. We also compare the power efficiency for the edge and the data center domain. Here, we define edge domain with a less than 20 billion model. And for the data center domain, we assume that more than 60 billion models. So for the edge domain, we compare a single LPU against NVIDIA's L4 device, and we for the 6.7 billion model, we got more than 40% efficiency than the GPU platform. For data center domain, we compare 8 LPUs against the 2 H100 devices with NVSwitch. And for a 66 billion model, we got more than 30% better power efficiency than the GPU platform. To compare the performance scalability, we compare our HyperAccel Orion against NVIDIA's DGX A100 with a faster transformer library. And we changed the number of devices from 1, 2, 4, and 8 devices and measured the performance. And as you see in this graph, our server shows very linear performance scalability from 1 device to 8 devices with the average rate of 1.76 times. On the other hand, GPU platform's performance gets saturated when it has more devices, like 4 devices and 8 devices. Furthermore, our platform can be extended up to 20 LPUs per server, proving our platform has much better scalability than the GPU platform. So now, let me show you a couple of demos from our server. So the first one is about the LPU scalability when they're generating 100 short sentences. So the left side is the single LPU, and the right side is the 8 LPUs. And as you can see, the 8 LPU can perform much faster. It's about 6 times faster, proving the scalability of our system. Next is we implement the real-time chatbot application on our Orion Accel Orion server. So currently, the users are typing the input queries on the prompt. I think the video doesn't show you very well, but it actually generates the, this is actually, right, something like this. The Orion actually generates the output token really fast. Maybe we can try once more. So now the user gives you an input query on the prompt, and you can see the Orion generates the output tokens really fast. This is the input from human, and this is the output from our server, showing you very reliable and fast experience. This is vastly different from current OpenAI service. So this actually proves that our server is ready for Gen AI application and service. So we are building Gen AI server cluster based on our Orion servers. This is a rack scale server solution for Gen AI services. We use a single dispatch server and use multiple of our Orion servers as LLM backend. And we try to focus on enterprise LLM service such as healthcare and education. And this on-premise server rack solution will be available in November 23, which is this month. So if you're interested, please let us know with the contact mail. The second product that we are working on is the LPU silicon IP. As I emphasized, this LPU is a highly scalable processor solution, and we want it to be first and the best solution for the Gen AI models. And we try to make it a product portfolio so that we can cover low-power devices up to high-performance accelerators. We also plan to have silicon prototype early next year. To conclude, we open a new AI era by building silicon chip and infrastructure for generative AI. Thank you.
Thank you very much for the wonderful presentation, Professor. I believe we have 5 minutes to receive some questions from the floor. So if there are any questions, please feel free to raise your hand.
Thank you for the great presentation. And I want to ask, my first question is about the software stack. So how does the very high level large language model is defined? Is it defined using some existing ML framework like PyTorch or TensorFlow, or is it defined using some custom language or other language?
Yeah, is the end of your question, or? Okay, so
I have.
Okay, go ahead, please.
Yeah, and second question is about the parallelization. So you said that you consider about the intra-layer parallelism, and so I want to ask, how about the inter-layer pipeline parallelism?
Okay. Yeah, thank you for your great question. So the first one, we actually use very public format. So if the user describes the model with the Hugging Face format, that's actually Python-based, I think, then our software stack can handle it. So that is through the Hugging Face format. So that was the answer for the first question. And for the second question, I believe that you asked about the a little bit more detailed model parallelization layer. So we apply intra-layer parallelism. What that means is that we partition each layer, but we only apply this only for the self-attention and feed-forward network because they are worth partitioning. The other things are not actually worth partitioning because the overhead for that is large. So for self-attention layer, we actually apply headwise partitioning. And the feed-forward network, we use very simple column-wise partitioning.
Thank you for the presentation. I'm glad that your development is going well and also your company is growing. And your product is basically presented as an accelerator solution for LLM.
Right.
And I guess you assume the current transformer-based network architecture. And if you talk to probably cloud service providers like Azure, then I guess they might ask the question about the flexibility of your hardware. I mean, the AI continuously evolves, and so would you like to comment on the flexibility aspect of your solution?
Right. That's a very nice question. So our platform is really specialized platform for Gen AI models, transformer-based Gen AI models, but we do have flexibility inside of it. But we are kind of focused on the Gen AI models. The model part is important. So we actually expect that the future processing will be model-based, not the operation-based. So that's the reason why we get model-level description as an input. We only expose that level to the user. User only gives us the model description, and they give us the input tokens and some algorithmic parameters, and then we give the output tokens back to the users. So that is the kind of flexibility that we can provide. But for the transformer-based generative model, we try to support more and more models. There are subtle differences and quite big differences even inside of the transformer-based models. So for example, for Llama, the normalization, GPT normalization, those are different. But we support both of them, so we are trying to expand our scope a little bit further, but not like general AI, like including deep learning. But we do have some plans to add image capability. So that's our plan.
Thank you for very interesting talk. So as far as I know, your current accelerator is based on the FPGA, right?
Right.
So from that, you can have some flexibility to accommodate the newer algorithms. So your next stage will be you will use that ASIC, right?
Right. Yeah.
So in that case, you can lose your flexibility somewhat.
Yep.
And then that is the first question, and the second question is that how much performance can be improved by using ASIC? So
okay. Yeah. Thank you for a great question. For the first question, that actually related to our business model. So our business model, the very first one is the server appliance, and we target this into data center market. And as you mentioned, we have some flexibility to add here. So since the algorithm space is also changing, we're going to leverage this flexibility for data center market. So this is a more like top-down approach. We make the entire system that can be used in data center domain at the system level first, and we actually get a lot of feedback from AI companies. They need more token sizes, and they need this kind of algorithm and such. So we are kind of adapting that. And having very mature hardware accelerator, our strategy is that we harden this into silicon IP so that it can perform well on the devices. So that's our kind of strategy. And the second question, since this is memory-bounded application, the entire system performance is actually bounded by the peak hardware memory bandwidth. So even though if we actually just translate this into ASIC with the same memory bandwidth, then we may have the same performance. but maybe we can reduce the power. That's one thing. Another thing is we can actually consider about more logic, something like image side and the batching side. We can improve that with the ASIC implementation.
Thank you very much for all the questions and the answers. Ladies and gentlemen, let's give Professor Kim another big round of applause for the wonderful session. 감사합니다. Now, ladies and gentlemen, this concludes the first session of the CE session. Ladies and gentlemen, distinguished guests, welcome back to the session. The second session of the breakout session will begin right now. As the presenter of the second session, we have Mr. Seungwon Lee, the VP of Technology from Samsung Advanced Institute of Technology, the SAIT, and Mr. Young-Hoon Sung, the VP of Technology from SAIT as well. They will both be presenting in Korean, so those of you who need interpretation services, please tune into channel 4 for English. Thank you very much. Then, without further ado, let's meet our first speaker, Mr. Seungwon Lee, the VP of Technology from SAIT, up to the stage. Ladies and gentlemen, please greet him with a big round of applause.
예, 지금 말씀드렸듯이 이번 수업부터는 한글로 이야기하겠습니다. 그러니까 많은 관객분들도 한국분이고 저도 한국인이라서 외국분들한테 동시 통역을 부탁드리고요. 오히려 저 메시지가 정확하게 전달되기 위해서 한글로 이야기하도록 하겠습니다. 일단은 제가 여기에 서서 발표하게 돼서 무척 영광스럽게 생각하고요. 저는 아까 소개했던 대로 세이트에서 근무하고 있고 최근에 한 6년 동안은 뉴럴 프로세서 또는 프로세싱 인 메모리라고 불리우는 스페셜한 하드웨어에서 올라가는 소프트웨어를 하고 있었습니다. 그리고 원래는 제가 여기 이제 농담을 약간 넣는데 영어 버전이라 한글에서는 농담이 없어요. 그래서 한 가지 하는 거, 제 이름이 이승원입니다. 제 이름은 기억하기 쉽게 하는 방법은 거꾸로 불러보면 기억하기가 쉽습니다. 예, 오늘 제가 말씀드릴 얘기는 머신러닝 포스필드라는 건데요. 이거는 AI를 가지고 앞에서 여러분들이 이야기했었던 라지 시뮬레이션을 어떻게 가속할 수 있는지 이에 대한 이야기를 하도록 하겠습니다. 이 그림은 지금까지 나와 있는 슈퍼컴퓨터의 모습입니다. 여기서 제가 전달하고 싶은 메시지는 두 가지인데요. 한 가지는 우리는 이제 엑사스케일 컴퓨팅이 되는 기계를 가지고 있습니다. 컴퓨팅을 엑사급으로 할 수 있는 걸 가지고 있게 되고요. 또 한 가지 여기서 가져야 될 메시지는 1922년부터 지금까지 나왔던 모든 슈퍼컴을 더해도 우리가 지금 엑스하고 얘기하는 프론티어의 3분의 1밖에 되지 않습니다. 그러니까 그만큼 컴퓨팅의 증가는 많이 이루어지고 있습니다. 이 그래프는 GPT-2가 나오면서부터 지금까지 어떤 종류의 라지 랭귀지 모델들이 나왔는지를 X축은 시간, Y축은 사이즈로 보여드리고 있는 것들입니다. 보시는 것처럼 현재까지 약 60개에 달하는 AI 모델들이 벌써 릴리즈가 되고 있고요. 한 가지 재미있는 사실은 이 모델들의 평균 사이즈를 다 구하면 180빌리언이 됩니다. 처음에 GPT-3가 나왔을 때의 사이즈와 비슷합니다. 이건 이제 저희 쪽 이야기입니다. 세이트는 알고 계신 분도 있을 수 있겠지만 1000개의 A100 GPU를 가지고 성능을 재는 버트모델 성능을 재는 MLFF에서 2021년부터 1등을 해오고 있습니다. 이렇게 지금 1000개의 GPU를 가지고 트레이닝을 하는 데 있어서 시간을 세계에서 가장 빠르게, 심지어는 엔비디아 DGX보다 빠르게 해놓고 있는데요. 이렇게 하게 된 이유 중에 제일 큰 거는 저희가 조금 더 큰 라지 배치로 트레이닝을 할 수 있게 만들었고, 그때 필요한 하이퍼 파라미터 튜닝을 사람이 하지 않고요. 저희는 AI를 써서 하이퍼 파라미터를 찾아냈었습니다. 그래서 이미 저희가 쓰고 있는 환경에서도 사람이 하는 것보다는 실제로 AI를 통해서 좀 더 많은 일을 걷어내고 있습니다. 조금 제가 이 슬라이드 준비를 잘못해갖고 동영상에 보여주면 좋겠는데 저희가 그럼 넥스트 스텝 하는 걸 말씀을 드리겠습니다. 여기 가운데 있는 그림은 흔히 얘기해서 반도체 공정 중에 엣지 공정에 해당하는 것을 시뮬레이션 하고 있는 겁니다. 이 시뮬레이션을 하기 위해서는 이 시뮬레이션 동영상에 좀 보이면 좋았을 텐데 위에서 HF라고 불리우는 원소를 쏘아서 반응을 일으켜서 밑에 있는 서피스를 조금씩 깎아내는 작업을 하는 시뮬레이션을 지금 하고 있는 것들이고요. 실제로 저희가 이 시뮬레이션이 된 걸 확인하는 방법은 오른쪽에 있는 그래프처럼 그 반응이 일어나는 계층의 두께가 점점 깊어지고 있는 것을 봄으로써 이것을 확인할 수 있습니다. 물론 아직까지 지금 여기서 말씀드린 이 시뮬레이션이 저희 회사에서 반도체 공정에 직접 사용하고 있지는 않습니다. 하지만 저희의 목표는 이러한 시뮬레이션을 실험을 하지 않고 시뮬레이션을 통해서 공정 레시피를 개발할 수 있게 만드는 것을 목표로 라지 스케일 시뮬레이션을 삼성 안에서 진행을 하고 있는 것입니다. 지금부터 간단히 MD 시뮬레이션이 무엇인지 말씀을 드리겠습니다. MD 시뮬레이션을 불리우는 것은 인풋은 간단합니다. 인풋은 어떤 타입의 원소를 사용하는지, 그 다음에 그 원소의 위치 정보가 어딘지의 정보만 가져가고 XY 좌표로, XYZ 좌표로 들어가고 그걸 가지고 이전에 우리가 고전역학에서 배웠던 포텐셜을 계산을 하는 식을 가지고 계산을 해가지고 시스템 전체가 갖고 있는 에너지, 그 다음에 그 에너지를 가지고 각각의 아톰들이 가지게 되는 포스를 계산하는 게 앞에 보셨던 MD 시뮬레이션이고요. 이것을 클래시컬한 포텐셜이 아니고 좀 더 정확한 DFT라 불리우는 아비오 이니셜 기법으로 통해서도 시뮬레이션을 할 수 있게 됩니다. 그럼 이런 시뮬레이션을 실제 저희 앞에서 보여드렸던 반도체 공정에 쓰려면 아직은 갭이 큽니다. 여기 그래프에서 X축이 실제로 시뮬레이션에 되는 사이즈고요. Y축이 필요한 시뮬레이션을 수행해야 될 시간입니다. 이렇게 보시면 알겠지만 현재 앞에서 보여드렸던 DFT 또는 MD, 클래시컬 포텐셜을 통해서 MD 시뮬레이션을 하는 경우에 있어서는 실제 저기 파란색 박스로 위에 점선으로 표시된 실제 원하는 리퀘어먼트들의 갭이 큽니다. 즉 몇십만 배 이상은 더 가속을 해야 가능하게 쓸 수 있게 되는 것이고요. 그리고 상대적으로 지금 보면 클래시컬 포텐셜이 DFT에 비해서 성능은 좋지만 DFT가 여기 보시는 것처럼 상당히 정확도가 좋고 특히 가장 중요한 거는 실험을 하지 않고도 실험을 하지 않고 시뮬레이션을 할 수 있는 장점을 가지고 있습니다. 하지만 반대로 컨스트레인트는 적혀놓은 것처럼 컴퓨터에 필요한 연산량이 너무 크다는 거죠. 그래서 오늘 얘기하고 좀 머신러닝 포텐셜이라고 불리우는 건 뭐냐면은 앞에서 설명드렸던 아톰의 표현을 받고 그 다음에 그 아톰의 에너지와 포스를 계산할 때 앞에 말씀드렸던 DFT나 또는 클래시컬 포텐셜을 사용하지 않고 AI 모델을 통해서 이 계산을 하겠다. 어프로시메이션이죠, 일종의. 이렇게 하겠다는 것이 목표가 됩니다. 이렇게 되면 저희는 무엇을 가질 수 있게 되냐 하면요. 왼쪽 그래프에서 보시는 것처럼 현재 DFT의 정확도를 가지는 MD는 없습니다. 그걸 DFT의 정확도를 갖는 MD를 만들고요. 그 다음에 DFT가 갖고 있었던 원래 문제점인 그 오더 오브 N 상승인 컴퓨테이셔널 코스트를 오더 오브 N으로 낮춰서 할 수 있는 게 되고요. 현재까지 저희가 해놓은 건, SAIT에서 하고 있는 거는 이렇게 AI를 사용해서 DFT의 정확도를 갖는 아톰의 시뮬레이션의 개수를 저희가 여기 적힌 10만 개 아톰까지 수준까지 늘리는 것을 해보고 있습니다. 그러면은 이런 ML 포텐셜을 처음 한 건 아닙니다. 이 ML 포텐셜 자체는 2007년에 벨로어가 쓴 논문이 처음이었고요. 이 그래프에서 보시는 것처럼 이 논문에 대한 인기는 최근 들어서 급증을 했습니다. 이렇게 된 건 크게 두 가지 원인이 있는데, 한 가지는 여기 보시는 것처럼 저 위에 그래프에 있는 것처럼 알파고가 나온 것이 하나 가지가 있고요. 처음에 이 머신러닝 포텐셜이 나왔을 때는 밑에 있는 그래프를 보시는 것처럼 이미 학습할 때 사용됐던 모델을 키우는 것만이 가능하다고 생각을 했었었는데 최근 연구 결과들이 리포트가 되고 있는, 증명이 된 것은 아니지만 리포트가 되고 있는 것들은 우리가 한 가지 타입의 모델을 가지고, 물질을 가지고 학습을 시켜놓은 것들을 왼쪽 그래프에서 보시는 것처럼 여러 가지 다른 형태의 변형에 대한 물질에 대해서 어느 정도 예측이 가능하다. 즉 하나를 잘 만들어서 학습을 시켜놓으면은 다른 모델에 어플라이 할 수 있는 게 가능해져 보인다라는 것이 밝혀지면서 좀 더 머신러닝 포텐셜에 대한 인기가 증가하고 있습니다. 그러면 이 머신러닝 포텐셜을 하는 데 있어서 AI 측면에서 볼 때 무엇을 해야 되는지 잠깐 말씀을 드릴게요. 기본적으로 머신러닝 포텐셜은 어떤 걸 가정하고 있냐면 각각의 엘리먼트 아톰들의 에너지를 계산해서 그것을 다 더하면 전체 시스템의 에너지가 될 수 있다는 믿음에서 시작을 하고 있는 거고요. 그렇게 하려면은 우리가 흔히 그 물리 법칙을 하는 것이 지켜져야 됩니다. 즉 아톰의 위치가 돌거나 아톰의 위치가 반대로 대칭이 되거나 또는 퍼뮤테이션이 될 경우에도 전체 에너지는 변경이 없어야 되고요. 이거는 이제 인베리언스라고 부릅니다. 그렇지만 저희가 일반적인 AI 모델 같은 경우에 이러한 인베리언스를 유지시켜주기가 쉽지 않습니다. 그래서 이런 포텐셜, 머신러닝 포텐셜이라는 AI 알고리즘의 경우에는 어떻게 이런 인베리언스를 지키는가가 매우 중요하게 되죠. 현재까지 나와 있는 머신러닝 포텐셜은 크게 두 가지 타입으로 나눌 수 있습니다. 첫 번째 타입은 왼쪽에 보시는 디스크립터 타입이라고 부르는 머신러닝 포텐셜인데 이 경우에 있어서는 앞에서 말씀드렸던 인베리언스를 만들기 위해서 우리가 알고 있는 XY 좌표인 코디네이트를 각속도, 그러니까 레디어스하고 앵글로 바꾸는 각속도로 바꿔서 인베리언스를 제공을 하고요. 그걸 통해서 뒤에는 우리가 흔히 알고 있는 티피컬한 AI 모델을 사용해서 포텐셜을 계산하는 방법을 씁니다. 이 방법 같은 경우에 있어서는 기존 AI 모델을 쓸 수 있다는 장점은 있지만 반대로 조성하는 물질을 구성하는 원소의 종류가 바뀌거나 조성이 바뀔 때마다 디스크립터를 다시 만들어야 되는 문제가 발생을 하고요. 이 디스크립터는 일반인이 만들기는 어렵고 물리 지식을 잘 갖고 있는 전문가분들만이 이 디스크를 만들 수 있다는 단점을 가지고 있습니다. 이것을 바꾸기 위해서 새로 요즘 나오고 있는 것이 오른쪽에 있는 그래프 형태입니다. 이 그래프 형태 같은 경우에는 각각의 지금 푸른색이나 노란색으로 표현된 점들이 아톰이 되고요. 그 사이 거리를 표시하고 그 다음에 근처에 있는 것들을 그래프 사이에 노드 사이에 메시지 패싱을 통해서 지오메트리의 정보를 가져가면서 아까 말씀드렸던 인베리언스를 유지하게 만들어 버립니다. 이렇게 되면은 만들어야 될 디스크립터 엘리먼트 각각의 기본적인 타입만 만들게 되면은 콤비네이션에 대해서 어느 정도 자유롭게 만들 수 있게 되고요. 또 한 가지 좋은 특징은 이 그래프에서 보시는 것처럼 이 그래프에 보시면 저 빨간색 박스로 표현되어 있는 것이 학습 구간에 학습한 겁니다. 지금 모델을 만들 때 학습 데이터는 저 빨간색 구간에 있고요. 그 다음에 빨간색 박스 바깥쪽은 학습이 되지 않은 영역입니다. 이거는 저 위에 있는 분자에 하나의 아톰이 가까이 갈수록 에너지가 어떻게 변하는지 보여주는 거라서 보시는 것처럼 그라운드 트루스는 DFT로 계산을 한 건데요. 그라운드 트루스의 값을 얼마나 잘 매칭하나 좋은가를 보여주는 것인데요. 지금 보시는 것처럼 같은 데이터를 갖고 학습한 디스크립터 방식과 메시지 패싱 방식이 있을 때 메시지 패싱 방식으로 했던 그래프 방식으로 디스크립터 방식보다는 그래프로 한 것이 조금 더 아웃 오브 박스, 즉 가르쳐주지 않은 곳에 있어서 예측력은 더 좋은 것으로 판단이 되고 있고요. 이것도 아직 증명된 건 아니지만 실험적으로 계속 보여지고 있어서 현재는 많은 일들이 이 그래프를 가지고 하는 것들 위해서 진행되고 있습니다. 그래서 보시는 것처럼 최근에 상당히 많은 연구들이 그래프 기반의 머신러닝 포텐셜로 진행되고 있고요. 그거에서 디퍼런스는 노드에다 어떤 정보를 두는지, 엣지에다가 어떤 정보를 두는지 등에 의해서 결정이 납니다. 그 다음에 여기서 한 가지 더 말씀드리면 이 그래프를 가지고 머신러닝 포텐셜을 인퍼런스를 하면은 기존에 우리가 사용하던 머신러닝 인퍼런스하고 좀 다른 게 발생하는데요. 뭐냐면은 보통의 인퍼런스라 그러면 인풋이 들어오고 아웃풋이 한 번 나오고 우리가 포워드만 하면 끝이 나지만 이 머신러닝 포텐셜을 갖고 있는 그래프 네트워크인 경우에 있어서는 어떻게 되냐면은 포워드 패스로 가면서 시스템 전체의 에너지를 구하고요. 그 다음에 아까 제가 말씀드렸던 각 아톰별로 에너지를, 포스를 구하기 위해서는 반대, 백워드를 한번 돌립니다. 즉, 인퍼런스이지만 포워드와 백워드가 다 존재하는 인퍼런스가 됩니다. 그걸 통해서 첫 번째 포워드에서는 토탈 시스템 에너지를 구하고요. 뒤로 오면 백워드일 때 각 아톰에 들어가는 포스를 계산하는 형태로 되는 것들이 이 ML 포텐셜의 특징입니다. 저희는 앞에 말씀드렸듯이 반도체 공정에서 필요한 머신러닝 포스 필드를 연구하고 싶습니다. 그걸 저희 혼자 할 수 있다고 생각을 하지 않고요. 그래서 앞에 보였던 다양한 형태의 여러 그래프들을 이밸리에이션을 하기 위해서 여기 보시는 대표적으로 반도체 공정에서 반도체에서 많이 쓰이는 물질 데이터 두 개를 아래에 보시는 것처럼 데이터셋으로 만들었습니다. 이 데이터셋을 한 가지 주의해서 보실 거는 여기 OOD라고 써 있는 테이블은 학습되지 않은, 아까 그래서 빨간색 외부에 해당하는 직접 학습되지 않은 영역에 대한 것을 이밸리에이션 하기 위한 데이터셋이고요. 이걸 통해서 우리가 만든 지금부터 우리가 이밸리에이션 모델들이 실제로 바깥쪽, 박스 바깥쪽을 얼마나 잘 예측을 할 수 있는지, 그 얼마나 활용할 수 있는지 보기 위한 지표까지 같이 넣어놓은 것이 보통 보시는 데이터셋과는 다르게 만들었습니다. 이걸 가지고 앞에 보여드렸던 여러 가지 그래프 기반, 여기는 디스크립터 기반은 없습니다. 그래프 기반의 모델들에 대해서 에너지의 정확도와 포스의 정확도를 표현한 그래프가 이쪽에 있는 것입니다. 여기서는 기본적으로 낮을수록 더 좋은 걸 보여주고 있는 그래프고요. 보시는 것처럼 정확도 측면에서는 뭐 다임랩스라고 하는 것 또는 갭넷T라고 하는 것이 조금 더 애큐트한 것을 보여드리고 있고요. 반대로 그 잼넷의 변형인 잼넷DT라고 하는 경우에 있어서는 상당히 밑에 쪽 그래프를 보시면 아는데요. 상당히 인퍼런스 시간이 짧게 걸리는 것들로 표현되고 있습니다. 그래서 그렇지만 이제 여기서 보면은 어느 게 제일 좋다, 제일 나쁘다고 얘기하기는 조금 어렵고요. 아직까지는 이 부분에 있어서 조금 더 많은 연구가 있어야 될 것 같습니다. 저희는 지금까지 말씀드렸던 이 페이지 때문에 앞에다 그렇게 많은 얘기를 좀 써놨던 건데요. 일단은 여기서 말씀드렸던 이 모델 이베이션 결과하고 그 데이터를 만든 것은 다가오는 유집스에서 발표가 될 거고요. 또 한 가지는 여기에 나와 있었던 지금 말씀드렸던 모든 데이터 셋하고 그 다음에 모델을 트레이닝하고 이베이션 프레임워크는 위에 보시는 GitHub에 올려놨습니다. 그래서 이베이션을 할 수 있게 되고 여기서는 저는 두 가지를 말씀드리고 싶은데요. 한 가지는 여기서 나오고 있는 여기서 우리가 필요한 저희가 필요로 생각하고 있는 이런 데이터셋을 가지고 좀 더 빠르게 만들 수 있는 머신러닝 포텐셜 연구도 필요하고요. 또 컴퓨터 엔지니어링 하는 입장에서 보면은 이거는 앞에서 여태까지 많은 스피커들이 말씀하셨던 트랜스포머 기반의 모델과는 다른 모델입니다. 일단은 그래프 형태로 되어 있고요. 그래프에 있는 모든 엣지가 한 번씩은 다 돕니다. 그 다음에 네트워크의 동작도 포워드만 있는, 인퍼런스이긴 하지만 포워드만 있는 게 아니고 포워드, 백워드가 존재하고요. 얘는 시뮬레이션을 한 번 시뮬레이션 피코나니 세컨드로 시뮬레이션 된 거를 초단위까지 가기 때문에 수백만 번 이터레이션을 돌아야 되기 때문에 그만큼 이피션트도 중요합니다. 이번에 이 세션은 아니고 옆에 세션에서 AI 챌린지를 했었고요. 그 AI 챌린지에서는 이 문제를 가지고 더 정확한 AI 모델을 만드는 걸 챌린지를 했습니다. 그리고 오늘 이따가 저희 세션이 끝나고 나면은 컴퓨터 엔지니어링 챌린지 시상을 할 건데 이번에는 람마 가지고 시상을 하게 됐는데요. 언젠가는 여기서 밝혀진 뉴럴 그래프 모델을 가지고 얼마나 빨리 인퍼런스를 할 수 있는지도 챌린지 문제가 될 수 있을 거라 믿습니다. 제 마지막 페이지입니다. 저희가 이런 일을 하는 거는 실제로는 이 그램에서 맨 왼쪽에 있는 웨이퍼 스케일의 공중에 쓰고 있는 걸 하고 싶은 겁니다. 그래서 저희는 이거를 이제 컴퓨테이셔널 마이크로스코프이라고 부르는 건데요. 그래서 DFT의 정확도를 가지고 있으면서 웨이퍼 스케일까지 할 수 있는 걸 해보려고 하는 것들이고, 지금 제가 설명드린 이 중에 첫 번째 단계, DFT 정확도를 가지고 MD 수준의 시뮬레이션을 할 수 있는 정확도는 저희가 지금 본 거고요. 그렇게 하기 위해서 이걸 좀 더 키우는 거고, 다음 스텝은 아마도 AI를 써서 서로게이트라고 불리는 이유는 중복되는 시뮬레이션을 줄여서 스케일을 더 키울 수 있는 방법을 연구를 해야 될 것으로 보이고요. 이렇게 만들고 있는 커지는 AI 모델을 가속하기 위해서는 밑에 적어놓은 것처럼 프로세싱 메모리 또는 프로세싱 리어 메모리를 통해서 메모리 밴드위스를 확보를 하고, 그 다음에 CXL과 같은 새로운 테크닉을 통해서 메모리 커퍼시티를 증가시킬 수 있는 방법으로 발전이 되면 언젠가는 저희가 DFT 정확도를 갖고 있는 시뮬레이션을 통해서 웨이퍼를 만들지 않고 웨이퍼 안에서 문제가 어떻게 될 건지, 그 웨이퍼를 만들려면 어떤 공정들이 필요한지 알 수 있을 거라고 생각하고 있습니다. 예, 여기까지 해서 제 발표는 모두 마치겠고요. 혹시 질문 있으실까요?
네, 소중한 발표 감사합니다. 질문이 있으신 분들은 손을 들어주시면 저희가 마이크 전달 드리도록 하겠습니다.
네, 안녕하세요. 다름이 아니라 DFT 같은 경우에는 사실 이제 제도 K에 의한 계산이고, 실제 물질 같은 경우에는 사실 저희들은 상온이나 아니면은 저온에서 이렇게 계산하게 되는데, 실제로 이와 같은 포텐셜도 그대로 이렇게 적용했을 때 이런 온도 문제나, 그리고 사실 아까 말씀하셨던 하프니um 옥사이드 같은 경우에도 실제로 DFT라고 하더라도 약간 좀 계산에 약간 오차가 있는 부분도 있고, 그래서 이런 부분들도 어떻게 극복하시려고 하시는지 궁금합니다.
예, 좋은 질문. 제가 좀 논문에 있는데 뺐던 내용인데요. 그러니까 저희가 이것을 지금 이제 DFT를 정답으로 보는 거는 지금 예제가 있었고요. 실제로는 시험 게이트하고 맞춰봐야 됩니다. 그래서 실제로 SAIT 안에서는 지금 저희가 몇몇 과제와 협업을 하면서 실제로 시뮬레이션 나온 결과가 지금 보셨던 에너지하고 포스 말고도 또 여러 가지 물질 특성들이 있습니다. 그런 것들 다 맞출 수 있게 해서 다시 업데이트를 하고 있고요. 그 다음에 DFT만 사용하지는 않습니다. 예, 지금 잠시 말씀하신 대로 DFT는 되게 약간 제한적인 형태에서 쓸 수 있고, 그 케이스 바이 케이스에 맞춰서 데이터를 더 만들고 준비를 해서 하고 있고요. 현재로서는 그렇게 하고 있습니다. 그래서 저희도 여기서 말씀드린 안에서 내부적으로는 지금 이제 시뮬레이션, 그러니까 시뮬레이션뿐만 아니고 시험까지 데이터를 같이 넣어서 맞춰서 데이터를 하고 있고요. 다음번 발표 때는 좀 그 결과까지 같이 얘기했으면 좋겠습니다. 예, 감사합니다.
질문 없으시면 여기서 마치도록 하겠습니다. 수고해주신 이승원参谋님께 다시 한번 큰 박수 부탁드립니다. Thank you very much for your valuable presentation. And next, we'll move on to the 2023 Samsung Computer Engineering Challenge Awards. The Samsung Computer Engineering Challenge is a competition aimed at domestic university and graduate students, and it was launched this year to increase interest among students in the field of computer engineering and to encourage them to continue their studies in this field. The Computer Engineering Challenge focuses on optimizing GPU for large-scale language models, Inference, and evaluated on a single topic, selecting one team as the first place winner, one team as the second place winner, and two teams as the third place winner. The winner team of the first place in each category will be awarded a prize of 10 million won. And for second place, 5 million won. And last but not least, the third place winner will be awarded with 3 million won and a certificate, respectively. Then, without further ado, we will now announce the winner of the GPUs for the LLM Inference section. First, I would like to invite Mr. Eunsoo Shim, the EVP of Samsung, to present the awards. 시상에는 연구센터장님이신 심은수 부사장님을 모시도록 하겠습니다. 큰 박수로 맞이해 주시기 바랍니다. Now, ladies and gentlemen, we will meet the winners on screen first. 먼저 화면으로 저희가 우승자들을 만나보도록 하겠습니다. 화면 띄워주세요. 네, 축하드립니다. 최우수상은 팀 H, 우수상 숑숑이, 장려상 이코, 그리고 비니네 축하드립니다. 무대 위로 모시도록 하겠습니다. I would like to invite all the winners up to the stage. Please greet them with a big round of applause. 네, 여러분 큰 박수 부탁드립니다. 네, 지금 차례대로 올라와 주시고 계십니다. 다 올라오시면 부사장님께서 시상을 진행하도록 하겠습니다. 그럼 바로 시작하도록 하겠습니다. We will now proceed with the award ceremony. 수상은 부사장님께서 수고해 주시겠습니다. 먼저 최우수상부터 수상하도록 하겠습니다. 팀 H 축하드립니다.
네, 김희훈님.
네, 축하드립니다. 여러분 큰 박수 부탁드립니다. 네, 다 받으셨고요. 우수상 숑숑이 축하드립니다.
예, 김진표님.
굉장히 귀여운 팀 이름을 가지고 있죠. What a cute team name.
축하합니다.
Congratulations once again. 장려상 발표하겠습니다. 이코 축하드립니다.
상훈님.
Congratulations.
축하합니다. 축하합니다.
네, 상금도 받아가시기 바랍니다. 감사합니다. 마지막으로 비니네 축하드립니다. Congratulations once again.
축하합니다.
네, 축하드립니다.
축하합니다.
네, 이 뜻깊은 순간을 사진으로 남겨보도록 할 텐데요. We will now proceed to the commemorative photo session. I will count to 3 and we will say AI together. 제가 하나, 둘, 셋 하면 다 같이 AI를 외쳐주시기 바랍니다. 네, 다 준비가 되셨나요? 이제 네, 가운데 서서 사진 촬영을 진행하도록 하겠습니다. 하나, 둘, 셋! AI! 네, 축하드립니다. Congratulations to all the winners. And thank you very much to Mr. Shim Eunsoo for your help. 네, 자리로 돌아가 주시면 감사하겠습니다. Thank you very much for your cooperation. And we are now reaching towards the end of the 2023 Samsung AI Forum. And before we conclude, I'd like to hand over my microphone to Mr. Eunsoo Shim, the corporate EVP, to deliver his closing remarks.
Yeah. Hello, everyone. What a day it was. We had the leaders, from the industry, from the world's largest cloud service providers to promising startups, and also we had leaders from academia and national labs. And I was thrilled to have the chance to hear their insight and also learn from them about the direction of the technologies in this AI era. Personally, I think I'm very fortunate to live in this time, observing the rapid development of AI technologies and also be part of it. I hope you had that excitement and also insight being shared by the distinguished speakers today, and carry that insight and develop your own new ideas coming forward. And hope this AI forum is a really productive time for all of you. And also I salute that you spend one day to share that exciting moment and also learning experience with all of us. I hope you go safely to your place and continue your journey in this AI technology development. Thank you.
Thank you very much for the warm remarks. Ladies and gentlemen, now this marks the end of the 2023 Samsung AI Forum.